Hello everyone, welcome to Basic Electronics Tutorials. In this video, I am going to discuss on the topic Zener Diode as a voltage regulator. Please note, in my previous video, I have explained the working principle of a Zener Diode as well as its VI characteristics. I would highly recommend you to watch that video first as a prerequisite to the topic of this discussion, and you can watch the same by clicking on the link shown in the top right corner right now. If you have already watched it, let us continue with this video. One of the biggest applications of Zener diode is that it can be used as a voltage regulator. The main function of a voltage regulator is to provide a rated voltage at the output despite changes in the input voltage. We know that a Zener diode is always operated in its reverse biased condition, where it generates a constant voltage across its terminals, and this voltage is called as the Zener voltage. A voltage regulator circuit can therefore be designed using a Zener diode to maintain a constant DC output voltage across the load in spite of changes in either the input voltage or changes in the load current. To understand this principle better, let us consider the circuit shown in figure 1, where a Zener diode is used as a voltage regulator. As you can see, it consists of a DC voltage source Vs connected in series with a current limiting resistor Rs and a Zener diode. Please note, the load resistor is connected in parallel with the Zener diode. Note the way in which the Zener diode is connected across the voltage source. Its cathode is connected to the positive terminal of the input supply and anode is connected to the negative terminal of the input supply. This type of connection is designed to operate the Zener diode in the reverse biased condition, where it breaks down and acts as an voltage source. The voltage across the load resistance is stabilized and is equal to the breakdown voltage Vz of the Zener diode. The role of the series resistor here is to make sure the current through the Zener diode is limited and is less than the maximum allowable value. Let us, for this discussion, assume that the input applied voltage is so high that the Zener diode breaks down in the reverse biased condition and starts conducting. Please note, the input voltage will be taken either from a rectifier circuit or a smoothing circuit. We will analyze this circuit to understand the voltage regulation operation under two conditions. The first condition is when the load is not connected to the circuit, and the second condition is when the load is connected. I will start with the first condition, that is when no load is connected to the circuit. When no load is connected, the value of IL will be 0. Please note that. Because the load current is 0, all of the circuit current now passes through the Zener diode, and this causes the Zener diode to dissipate maximum power. To make sure this circuit current does not damage the Zener diode, we have connected a series resistance Rs here. This series resistance will limit the current through the diode to a value less than or equal to the maximum permissible Zener current, thereby not letting it to get damaged. Therefore, the series resistance Rs is a very important component in the circuit and care must be taken while selecting its value. If the value of Rs is less than the minimum required value, then the Zener diode will dissipate maximum power and has a very high chance of getting damaged. So, in essence, when the load is not connected, the load current is 0 and the circuit current passes through the Zener diode now. Because this current is quite high, the Zener diode will dissipate maximum value of power. To make sure the Zener diode does not get damaged because of this high current, we connect the series resistance Rs. The series resistance is connected to limit the current through the diode so that it does not get damaged. The value of Rs plays a very important role and care must be taken while selecting it, because if the value of Rs is less than the minimum required value, then the Zener diode will dissipate maximum power and has a very high chance of getting damaged. Let us now consider the second case where the load is connected. Under this condition, voltage regulation can be achieved through two techniques. The first one is called as line regulation and the second one is called as load regulation. Let us now discuss about the line regulation first. In this case, the series resistance Rs and the value of the load resistance RL are both kept constant and all the variations in the voltage are attributed to the fluctuations in the input voltage. That is, in this particular scenario, the resistances Rs and RL are fixed and input voltage is varied. However, care must be taken so that the minimum input voltage is always greater than the Zener diode breakdown voltage. If the input voltage is less than the Zener diode breakdown voltage, the Zener diode will not break down and therefore it will not conduct. If the Zener diode does not break down and start conducting, then regulation cannot be achieved. For this particular case, the percentage regulation is given by the formula delta V naught, which is the change in the output voltage, divided by delta V in, which is the change in the input voltage, multiplied by 100, because this is in percentage. As I said, delta V naught is the change in the output voltage and delta V in is the change in the input voltage. So, we call this particular case as line regulation because it is the input voltage that is being varied while holding the load resistance value constant. So, in summary, in line regulation, the series resistance Rs and the load resistance RL are kept constant and the variations in the voltage are attributed to the changes in the input power supply. Care must be taken to make sure the input voltage is greater than the minimum input voltage required to reverse bias and break down the Zener diode. Otherwise, voltage regulation cannot be achieved. And lastly, the percentage regulation is given by the formula delta V naught divided by delta V in multiplied by 100, where delta V naught is the change in the output voltage and delta V in is change in the input voltage. Let us come back and discuss the second type of voltage regulation, which is the load regulation. In this case, the input voltage is kept constant and the load resistance value is varied. Since it is the load resistance that is being varied, this regulation technique is called load regulation. Let us assume that the input supply voltage Vs is greater than the reverse biased voltage required to break down the Zener diode in reverse biased condition, which we will denote it by Vz. Under this case, the Zener diode will start conducting and a constant output can be achieved across its terminals. The value of this voltage is equal to Vz. However, care must be taken so that the value of RL is maintained above a minimum value. If the value of RL is too low, then the circuit current will pass through the load as it will be the low resistance path and the Zener diode will therefore fail to break down and start conducting. And lastly, the percentage of regulation for the load regulation is given by voltage under no load condition minus of voltage under full load condition divided by voltage under full load condition multiplied by 100. Please note, all of these voltages listed here are DC output voltages. So, to summarize the load regulation technique, the input voltage is kept constant and the load resistance is varied. Assuming that the input voltage is greater than Vz, which is the breakdown voltage of the Zener diode in the reverse biased condition, the Zener diode will start to conduct and a constant output voltage can be achieved across the load terminals. However, care must be taken to make sure the value of the load resistance is maintained above a minimum value. If the value of RL is too low, the Zener diode will never break down and therefore no regulation can be achieved. And lastly, the percentage of regulation is given by DC output voltage under no load condition minus of DC output voltage under full load condition divided by DC output voltage under full load condition whole multiplied by 100. Please note this is in terms of percent. So, we now understand that a Zener diode can be used as a voltage regulator because of the principle of its working operation. A Zener diode, as we know, breaks down in the reverse bias condition at a certain reverse breakdown voltage, and once it breaks down, the voltage across its terminals will always be equal to the Zener voltage value, which is Vz. Once the Zener diode breaks down, the voltage across the load resistance will be kept constant and will be equal to the Zener voltage of the diode. Right? That is about a brief discussion on Zener diode as a voltage regulator. In my next video, I'll take up some numericals on Zener diode in the application of voltage regulation. So, stay tuned. Well, with that, we have come to the end of this video. If you like this video, kindly like and share this video and subscribe to my channel for more tutorials on basic electronics. Thank you for watching. Have a good day.